what you just saw there is a very famous example of what we call Newton's cradle, and more specifically, the law of conservation of energy. So, what we mean by the law of conservation of energy is that energy can neither be created nor destroyed. Instead, it can change from one form to the other. However, we know that Newton's cradle and eventually things on Earth, especially, are going to run out of energy, or at least that's the appearance, because some energy is not transferred exactly from one to the other. Whether we talk about a ball eventually coming to a rest, even if it's on a very slippery slope, it's going to eventually come to a stop. Whether we talk about the Newton's cradle, eventually those marbles are going to come to a stop. So why is that? Well, on Earth, we have something called friction. If we were to do these same experiments out in space, because there is so little friction, in fact, none, because it's all open space there, an object can fly through space with ease because it's not hitting molecules on the way by. So on Earth, with friction, these energy conversions aren't 100%. And we can see this a lot with what we call the ball bounce. So when we drop a soccer ball or a baseball or a basketball from, let's say, chest height, and we keep our hands straight out, we release it, we know that the ball doesn't come back to our hands. Even the most bouncy of things don't necessarily do this. And the reason for that is as that ball hits the ground, some of the energy as that ball flattens is going to be sent to and through the ground. And if we're standing next to that, especially with a basketball on a basketball court, we can feel that in what we call a vibration. So what's happening is the contact of that ball is sending the energy through the floor through little waves that we can feel as vibration. We can feel this when something heavy drops. And so the heavier the object, let's say we're doing like a weight that doesn't bounce at all, when we drop that thing, we can feel vibrations that much better because more energy is sent to and through the floor. So we call this collectively the law of conservation of energy. So what's happening is as that ball hits the ground, some of the energy that the ball has is being put on the ground or floor. So then when it bounces back up, it has lost some of that energy. And so let's say we dropped it at 5 meters, which was about 15 feet. When it bounces back, it's only at about 9 feet. And so some of that energy was lost. So after the drop, as we read here, how much of the gross potential energy does it have when it strikes the ground at 0 meters? Well, it's got 0 because it has flattened, or it says run out of energy. And so collectively, what we call this whole process is we call this the law of conservation of energy. And so in recap, we know that the higher we drop something, the greater the potential energy that it has. And it also means that when we drop it, it's going to hit the ground with greater kinetic energy. Because all of the potential energy is converted to kinetic energy throughout the fall. So this only works with falling objects. A roller coaster, however, as we'll talk about, is not a falling object. So with roller coasters, what we're doing is, so here we're looking at the top here. So obviously it takes a lot of energy to get this, with the belt here and the chain to get it to the top of the roller coaster. That takes a lot of energy. But if you've noticed, if you've been on a roller coaster before, after you get up that first mountain, sometimes you don't get those chains again. Instead, it uses that energy throughout. And as it drops, and we see this with like some of the experiments that we've done with ramps, as it drops, it's going to stay on those rails and use that energy to its advantage. And we can feel that especially at the bottom here. So we're at the top. We obviously will feel a lot of acceleration because it's the mass of the cart plus the people in it. And then that potential energy and kinetic energy carries with us to this mountain where now we don't need that chain. So in a roller coaster or a ramp situation, what we're doing is we're using the energy from the mass of the cart, from the pull of gravity, and instead of losing it, like crashing and bouncing it off the ground, we're using it to then climb another hill. So as we see, the energy, though, is not a perfect transformation. When we have a roller coaster and it's got the little wheels on the rails, even though like trains and roller coasters are very efficient, we know that there's going to be some friction. No matter how much oil we use, no matter what kind of metal we use, there's going to be some kind of friction. And so that's why, even though we use a lot of energy to get this roller coaster up here, eventually it's going to be lost because of that friction. So that's what we mean by no energy conversion is 100%. Instead, we will lose something in the form of some type of energy. So I just want to kind of throw some examples out there. I'm going to give you a couple of moments to think about each of these. Well, let's think about this. How do we get a light bulb to light, and why is some of that lost as heat? So first of all, a light bulb will start with electricity. So we plug it in, it gets electricity. We end with light, but we also get some energy lost as heat. When we touch a light bulb that's been on for a while, to the touch, it's going to feel hot. All right, let's try another one. A fan. Start with electricity, end with movement, waste, heat. A battery. Start with chemical. Let's say it's a remote control car. Ends with mechanical, waste, heat. A fire. Start with chemical energy, that'd be like the wood. Ends with light energy. Waste energy is heat. You're seeing a trend here. A lot of energy conversions, they are lost as heat. And it might be from friction, it might be from combustion, but most of the time, energy is lost in the form of heat. Let's think of another example. Swings, kind of like the pendulum. As a swing moves back and forth, the energy is converting from one form to the other. Why will the swing eventually stop? What is it transferred into? So hopefully we know that swings, there's usually chains at the very top. That's friction. Could be metal on metal. You have weight that is going to, you stop pumping your legs. Eventually you're going to end up at point B. But the reason for it is the friction in the chains up here. One more example, or a couple more examples, I should say. How about this one? You have someone that is using so this is a trampoline. They're jumping off this platform using the words gravitational potential energy, elastic potential energy, kinetic energy, and gravity. How would you say this is working? The boy up here has great gravitational potential energy. The elastic potential energy is in the trampoline. When he jumps, that then converts it into kinetic energy. Gravity is going to pull him down. Elastic energy is going to catch him and then push him back up. Now, eventually he's going to stop bouncing because there is going to be friction or loss of energy as he's hitting molecules on the way down or as he's hitting molecules on the way up. And one last one, using the words gravitational potential energy, elastic potential energy, kinetic energy, gravity. What is going to happen with this girl on the medicine ball? Well, she's probably going to fall on her butt or hit her head on the fridge or something. But same idea is that you are using elastic energy, gravitational energy, but eventually all things come to a stop. So this topic of our video today is a big idea. It is the law of conservation of mass. And as we know in science, a law versus a theory, a law is proven over and over and over again.